All right, Chemistry 111. We finished exam 2, and now we're on to chapter 5, which deals with gases. And we're going to take a look at gases in this lecture as well as the following lecture. After that, we'll be looking at thermodynamics, and then after that, we'll have our third exam. Anyhow, let's get started with chapter 5, which deals with gases. And if we take a look at the periodic table and we look at all the elements in the periodic table, you can see the elements that exist as gases at 25 degrees Celsius in one atmosphere, those are the ones that are highlighted in this teal color here. Okay, so anything that's in this teal color, these are gases at 25 degrees Celsius, which we call room temperature, in one atmosphere, which we sometimes call atmospheric pressure. Now, you probably noticed that I have two elements here circled in red, and that's because bromine and mercury are actually liquids at room temperature. And that means that everything else, all of these other elements here, these are all solids at room temperature. And so you can see that most of the periodic table is in fact solids, and very few elements are gases. Something else you should know is that some of the gases are diatomic. For example, when hydrogen is found by itself in nature, it's not found as H, it's found as H2. The same thing is true for nitrogen, oxygen, fluorine, chlorine. Okay, and it's also true for bromine and iodine. However, they are not gases, and we're talking about gases right now. So these ones exist as diatomic elements. And then over here in group 8A, we have the noble gases. Okay, so again, not a lot of elements that exist as gases, but they are all, of course, very, very important. And we're going to see these elements come up over and over during this chapter. Now, what about compounds that are gases, right? If I was to ask you, name me a gas, you guys, I'm sure that a lot of people would say carbon dioxide, right? This is a gas that all of us are making right now if we're alive. Anyhow, we're all making carbon dioxide. And you can see that we've got the elements over here. So these are the elements that were highlighted on the last slide, right? These are the elements in teal from the last slide. But when you look at compounds, there actually aren't that many compounds that exist as gases. In fact, most compounds exist as solids or liquids. Not a very big list here. You got things like carbon monoxide, which is sometimes called the silent killer. It's a byproduct of the combustion of gasoline. So when you start up your car, you form not only CO2, but you also form carbon monoxide. You have methane, ammonia, right? Other things like hydrogen sulfide, hydrogen cyanide. And you probably noticed that you have the hydrogen halides or the hydrohalides here, hydrogen fluoride, chloride, bromide, and iodide. And I had a student ask me a question about this maybe a few semesters ago. The student said, well, Mr. DM, I thought that HCl, I thought that that was hydrochloric acid. Well, when you have HCl in its pure form, it's actually called hydrogen chloride. And hydrogen chloride and hydrochloric acid are two very different things. Hydrogen chloride is HCl in the gaseous phase. Hydrochloric acid is what you make when you take gaseous hydrogen chloride and you bubble it through water. Okay? So when you have hydrofluoric acid or hydrobromic acid or hydroiodic acid, those are aqueous solutions of gas in water. Whereas hydrogen iodide, hydrogen fluoride, hydrogen bromide, these are all gases at room temperature. Okay. Something that's kind of interesting here is if you think about the average atomic mass of the air that we breathe, right? What is the air that we breathe made of? Well, it's mostly made out of nitrogen. It's about 78% nitrogen and 21% oxygen, 1% other. But the average atomic mass of the air that we breathe is around 30 grams per mole. So you've probably all tried inhaling helium at some time in your life. Now, helium has an atomic mass of around 4 grams per mole, so it's much lighter. And so the sound waves travel a lot faster. And if you inhale helium and then speak, you have a higher pitched voice. And if you you just do a Google or YouTube search of people inhaling sulfur hexafluoride. Well, sulfur hexafluoride has a molar mass that's significantly heavier than air. And so when you speak after inhaling sulfur hexafluoride, it gives you a deep voice like James Earl Jones or Darth Vader or Barry White or something like that. And it gives you a really deep voice. Anyhow, it's kind of interesting there. So again, some substances that are found as gases at 1 atmosphere in 25 degrees Celsius. This slide is not put here for you to just go here and memorize it directly. It's just to give you an idea of what compounds are gases, and they're compounds that we're going to see come up over and over and over, and elements that are going to come up over and over and over throughout this chapter and the class. Now, what about the physical characteristics of gases, right? If you go back earlier in the class, we talked about solids, right? If you have a solid or a liquid or a gas, well, the particles in solids and liquids, right? The particles are really packed closely together. Again, this is true for both the solid and the liquid phase. Now, we know that in the solid phase, there's no movement of those particles, but in the liquid phase, there are movement of the particles. They can slide past one another. But gases are something completely different, right? In a gas, the gas particles are going to assume the shape of the container they're in, and they're also going to take up the volume of whatever container they're in. Really? Yeah. If it's a small container or a big container and you have the same amount of gas, it's going to seek to fill that up. So what that tells you is that in a gas, the particles are going to be much further apart, right? They're going to be spread apart, okay? And since the particles are going to be spread apart in a gas, it stands to reason that they're going to be compressible, right? We are able to compress a gas, whereas solids and liquids are virtually incompressible. All right. What about how do gases mix? Well, if we mix gases together in the same container, they're going to mix completely and they're going to mix evenly to form homogeneous solutions of gases, right? Okay, what else? It says the gases have much lower densities than liquids and solids. Normally in chemistry, when we're reporting the density of a solid or a liquid, we report density in grams per milliliter or grams per centimeter cube. They both mean the same thing. However, we're going to take a look at the densities of some gases. And since the density of gases, there's so much less mass of a gas per unit volume, instead of using grams per milliliter, we usually use grams per liter. The reason why, again, is the number of grams in 1 milliliter of a gas, excuse me, is so small that you have densities that are like 0.0000, right? And you don't want to have that many zeros. It's just not practical. Now, what kind of gas is shown in here? This is bromine, okay? So if you have bromine, again, I told you that bromine is a liquid, but bromine at room temperature will be in equilibrium with bromine in the gaseous phase. In fact, if you open up a container with bromine in it, you'll see the bromine vapor start to come out of it immediately. But bromine has a reddish color, right? It's got a reddish color. Okay, it doesn't matter if it's in the solid phase or the gas phase. And so what do we see? We see that reddish color all throughout this volumetric flask, right? It seeks to take up the volume of the entire container. That's what a gas does. All right. Okay. And again, I should point out that what you're actually seeing here, this is bromine in the gaseous phase that's in that volumetric flask. A little bit of history about gases, and Mr. Dion certainly isn't a chemistry historian or anything, but if you ever wondered where the word gases comes from, I'm never going to ask you about this, but it's related to the spelling or pronunciation of the Greek word for chaos, okay? Right, because the particles are randomly dispersed, they can move freely, the particles of a gas. Sometimes they're called vapors, fumes, miasmas. Miasmas is generally used for things that smell bad. It's kind of a historical word that we don't use as much. What else? Air, again, is a common mixture of gases. And if you didn't catch what I said on the last slide, the air is made up of about 78% nitrogen, about 21% oxygen, and about 1%, we'll just call it other, things like methane and carbon dioxide. We talked about the shape and volume of a gas. We talked about compressibility. We talked about heterogeneous mixtures. You're probably all aware of the fact that gases can exert a pressure, right? If we think about blowing up a balloon for a party or something, maybe you squeeze the balloon and you know that the gas that you put inside a balloon exerts some kind of pressure on the walls of a balloon. Same thing occurs when you blow up a tire, say on your bicycle or an automobile. And what we're going to do tonight and in the next lecture is we're going to take a look at the properties of gases and the behavior of gases, right? How do they behave and what are their properties? And the way that we're going to explain the behavior and properties of gases is by treating them as what are called ideal gases. Now, you might be wondering, what is an ideal gas? Well, technically, theoretically, there's no such thing as an ideal gas, right? It's like an ideal human being. It doesn't exist, okay? We can try our best, but anyhow, so an ideal gas is summarized as such here, using the kinetic molecular theory of ideal gases. Okay, so let's take a look at how we are going to treat gases in this chapter. A gas, whatever it is, carbon dioxide, carbon monoxide, hydrogen, helium, whatever. The gas is composed of little tiny discrete particles, whether they're atoms or molecules, right? An example of a gas that's an atom would be something like, let's say, neon, that's just an atom, or a molecule, something like CO2, right? Okay, so those are gases. Now, what we do is we think about the gases, the particles of gas, we think of them as in rapid, random, continuous straight line motion. So have you ever seen the DVD side, right? We think of them as just barrel, 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 right? Bouncing off the walls of the container, so to speak. Okay, that was just my artist rendition. But we think of them as moving in random, continuous, quick, straight line motion. We also assume that the particles are far apart compared to their size, okay? So when we're looking at a gas, if this is a gas inside this black box that I've got here, what is it mostly? It's mostly empty space, right? It's mostly empty space with just a little bit of particles in here. Next, it says the ideal gases consist of particles that have mass but not volume. Okay, so all of these particles that we're looking at here, they have a mass associated with them, right? If we have matter, of course, it's going to have a mass associated with it. Mass, but no volume. Now, you might be thinking, Mr. Dion, that's crazy. If you have matter, of course, it's going to take up some kind of space. Yeah, that's true. You're absolutely right. That the gas particles do take up a space, but since the particles are so small compared to the overall volume of the gas, we consider them to be particles that don't have a volume. So we call them dimensionless points, okay? They're just little points that don't have any volume, but they don't have a gas. And if you're like, well, that doesn't make sense. Again, we're making an assumption here. I never said that was absolutely true, but it's an assumption that's going to hold true 99% of the time, okay? In fact, 100% of the time for basically everything that we're going to look at, okay? There's also one more thing that's not on here, and I'm just going to throw it in here. This is kind of my thing that I want to, and we're going to talk about it more later, but I just want to introduce it now, is that the particles, so we'll put here, gas particles, okay, not attracted to one another, What does that mean? It means, let's say you have these two gas particles here, they don't repel each other and they don't attract each other. Okay, they're not going to interact with each other. Now, again, that's an assumption that we're making. It's not entirely true, and it really depends on the gas. But it's an assumption that we're going to make when we're talking about what? Ideal gases. And the kinetic molecular theory of ideal gases is going to hold true for us 99.9% of the time in this class. Okay, so you don't have to worry about stepping outside of ideal gases a whole heck of a lot. Well, before we get into, really treating ideal gases, let's talk about the pressure of a gas. We have to define pressure, and pressure is defined as force per unit area. If you've ever blown up a car tire, you probably know that pressure in a tire, let's say you have a tire like this, the pressure is measured in PSI, which is the same thing, which means pounds per square inch, right? PSI. Well, what are pounds? Pounds is a measure of force, right? And what's a square inch? It's a unit of area. So there you go. Pounds per square inch represents force per unit area. And so that makes sense. Pressure is force per unit area. Now, what are the units of pressure that we're going to use in this class? Well, we're going to use all of the pressure units that you see here, okay? Every single one of these is going to show up. I noticed there's a mistake here. Instead of PA like this, it should be a capital P here. So this should be an uppercase P. You can fix that. So 1 PA, big P, uppercase P is equal to 1 Newton per meter squared. Now, if you read the textbook, it's got a more elaborate treatment of this, and it talks about the Pascal and things like that. But you can see that the Pascal is a unit of force, a Newton per meter squared, right? We have our force, which is our Newton, and we have our area here. Okay, so the Pascal is pretty intuitive. Well, you heard me talk about atmospheres earlier on, right? I said 25 degrees Celsius in one atmosphere. What's at one atmosphere? One atmosphere is the pressure, I'll put it here, pressure at sea level on the planet Earth, okay? So the pressure that's felt at sea level on this planet is one atmosphere. So you can imagine that in Colorado Springs, we don't feel one atmosphere of pressure, we feel less than that. But you see here that one atmosphere of pressure is equal to 760 mmHg. mmHg stands for millimeters of mercury, and it's also equal to torr. Now that's one of the funniest unit conversions you'll ever see in science, is that a millimeter of mercury is equal to a torr, okay? And you might be wondering, what are millimeters of mercury and what are torrs? Well, and why are they equal to one atmosphere? Well, let me tell you the story very quickly. What happened was there was a famous Italian scientist named Evangelista Torricelli, and what he did is he went down to the seaside, right, sea level, because Italy is surrounded, or a lot of Italy is surrounded by the ocean, and he took a tube, a glass tube that he had like this, okay? This is not to scale, this is Mr. Dion's rendition here. So he had this open-ended glass tube, and he had it filled with mercury, okay, like this. And then what he did is he took it and he inverted it into a dish of mercury. This is mercury right here, okay? And then what happened was he looked at the height of the mercury in that glass tube. And he measured the height of mercury and he determined that it was 76 centimeters. Now we know that there is 10 millimeters for every 1 centimeter, so that equals 760 millimeters. The column is filled with mercury, and so that's why we call that 760 millimeters of mercury. Now, why would that be equal to one atmosphere? Because what is the force that's holding the mercury up in that column? It's the force that's exerted down on the mercury in the dish here. It's atmospheric pressure. And so that is how those units came to be. That 760 millimeters of mercury is equal to the pressure on planet Earth at sea level, which is 101 atmosphere. And again, in honor of Evangelista Torricelli, we also call that unit the torr. So a millimeter of mercury is equal to a torr. Now, if you've studied pressure in physics class, you might have seen the Pascal more, and you might wonder what's the relationship between millimeters of mercury and atmospheres and torrs and pascals. Well, that conversion is shown right here, that one atmosphere is equal to 101,325 pascals, but more commonly, we're going to use one atmosphere being equal to 101.3 kilopascals, right? And you can imagine that there are 1,000 pascals, right? We have 1,000 pascals for every 1 kilopascal, okay? Pretty easy to put that one together there. Well, again, I don't expect you to have all of these memorized off the top of your head immediately. If you do the practice problems that I've listed, if you do all of those, by the time you're done, you will know that one atmosphere is equal to 760 millimeters of mercury, and you'll probably also have this memorized as well. With those in mind, let's see if we can try a practice problem here. It's not meant to be anything mind-boggling. It's just to see if we can use some dimensional analysis to do a pressure conversion. It says the pressure outside a jet flying at a high altitude falls considerably below standard atmospheric pressure, right? It's a low pressure when you get up high in the atmosphere. That's why they have to pressurize a cabin. It says, therefore, the air inside the cabin has to be pressurized to protect the passengers on the plane. What is the pressure in atmospheres in the cabin if the barometer reading is 688 millimeters of mercury? So a barometer is something that's used to measure atmospheric pressure. Okay, and if you've watched the weather segment of the news at all, you've probably heard the word barometer. You know, we're looking at the barometer and there's a low pressure system or a high pressure system. So again, a barometer used to measure atmospheric pressure. All right. We have a reading that is 688 millimeters of mercury, and we want to end up with the number of atmospheres. So we need some kind of conversion factor that's got millimeters of mercury in the denominator and atmospheres in the numerator. Well, if we look at our last slide, we see that 1 atmosphere is equal to 760 millimeters of mercury. So let's plug those numbers in. 1 atmosphere, 760 millimeters of mercury. Look at this. Millimeters of mercury cancel, and I end up with my answer, and I'm going to double check my math here with the calculator. So I have 688 divided by 760, and you should have 3 significant figures, and you should get 0.905 atmospheres. Okay, atmospheres. There we go. So again, you're in that jet. You're at a much lower pressure outside of the jet, but inside they pressurize it. They don't pressurize it all the way to atmospheric pressure, but they pressurize it enough so that it's comfortable for the passengers inside, and the pressure that's felt in atmospheres is 0.905 atmospheres. So about 90.5% of a full atmosphere. Okay, and again, we don't feel full atmospheric pressure here in Colorado Springs, so there's no, and we're perfectly happy, so there's no reason why you need to feel it in a plane. Okay, let's take a look at another example. You can see how, again, this would lend itself to a multiple choice question for your next exam very easily. It says the atmospheric pressure in San Fran on a certain day was 732 millimeters of mercury. What's the pressure in kilopascals? Well, let's start out. We've got 732 millimeters of mercury. We need to multiply this by some kind of conversion factor that's got millimeters of mercury in the denominator, kilopascals in the numerator, right? Because then millimeters of mercury would cancel and we would end up with kilopascals. Well, let's go back 2 slides and take a look. And we said that 1 atmosphere is equal to 101.3 kilopascals, but 1 atmosphere is also equal to 760 millimeters of mercury. There we go. So our conversion factor is going to be this right here. 101.3 kilopascals are in 760 millimeters of mercury. Let's go ahead and try plugging those numbers in. We've got our atmospheric pressure, 760 in millimeters of mercury. In kilopascals, it's 101.3. So we take 732 multiply by 101.3, divide by 760, boom. And you should end up with something that's got 3 significant figures, and we end up with 97.6 kilopascals. All right, there we go. So again, a barometer was used to measure atmospheric pressure, right? The pressure in the atmosphere. But if we want to measure the pressure of a gas, right? We talked about all these different gases that we might see in this chapter. What if we wanted to measure the pressure of helium or hydrogen or neon or some gas that we've made in the lab? Well, in order to do that, instead of using what's called a barometer, we use what's called a manometer. Okay, so you get a barometer, then a manometer. I've heard students call it a manometer, but I think it's actually pronounced manometer. So there's 2 types of manometers that we're going to be concerned with in our class. And our book doesn't go into great detail about manometers, so I'm going to talk about them a little more than the book does. You can have either what's called a closed tube manometer, which is where you have a gas in a bulb that's shown here. You have some mercury in a glass tube here that's connected to the gas, and then you have this stopcock here which keeps it all closed. Okay, so if you think about, what would the pressure of the gas be? Okay, well, if this end of the tube is closed, right, and there's just a vacuum up there, what's forcing the mercury to be higher on this side than it is on this side over here? It's the pressure of the gas, right? It's the particles of the gas that are pushing down on the mercury, which is causing it to rise up on the other side of the tube. So then it makes sense that when you have a closed tube manometer, okay, that the pressure of the gas, and you can't see it very well here, but the pressure of the gas inside the bulb is going to be equal to the height of the pressure of the or the height of the column. So it says pH, lowercase h, which, and let me just rewrite it here. The h just means the height of column of mercury in millimeters mercury. Okay, so you'd measure it in millimeters, and that would be the pressure of the gas. Okay, well, what if we have an open tube manometer? Right? What if we have an open tube manometer? When we have a closed tube manometer, and you can read more detail about this in the book. Again, it doesn't say a ton, but closed tube manometers are usually used when we have a gas that has a lower pressure than atmospheric pressure. Okay, so used, we'll put used for this scenario when the pressure of the gas is a low pressure. An open tube manometer, not always, but oftentimes it's used when the pressure of the gas is greater than atmospheric pressure. But it's not always true, and you're going to see that on the next slide, so I don't want to write that down here. So what would you do? Okay, well, if the pressure of your gas is coming from the gas that's in here, right, and it's pushing down on the column of mercury, okay, well, in the last example, we said, well, the pressure of gas comes from, or the height of the mercury that's right here comes from the gas particles pushing down on the mercury, which causes this mercury to rise. And that's cool. That's totally true. Right? You can even see that here. It says the pressure of the gas is equal to the pressure represented by the height of the column of mercury. But hold the phone. If this end is open, there's also atmospheric pressure pushing down here, right? The pressure of the atmosphere is pushing down. And so not only did the gas particles have to push against the mercury, but they also have to push against the atmospheric pressure. And so you have to add not only the pressure, or the represented by the height of the column of mercury, but you've also got to add the atmospheric pressure. Now, if you have the open tube manometer, and here you have, this is an open tube and this is an open tube here. There are two scenarios. Again, our book says that open tube is usually used when the pressure of the gas is greater than atmospheric pressure. So maybe I could write it here. Let me put usually used. Okay, I want to be careful what I say here. So usually, but not always, is when the pressure of the gas is greater than atmospheric pressure. Again, not all the time. Okay. Now, here's two open-ended manometers right here. Okay, again, one end is open, and so you got the pressure of the atmosphere pushing on the mercury. Now, if you've got the situation where the pressure of the gas is less than atmospheric pressure, that's this situation right here, the mercury is going to be pushed towards the gas sample, right? Because the gas particles aren't pushing hard enough compared to, or pushing as hard as the as atmospheric pressure. And so how would you measure the pressure of that gas? You would take the height of the column of the mercury, but then you would subtract the effect of the atmospheric pressure. Okay, so that's represented by this example right here. Okay, to measure the pressure of the gas, you would take atmospheric pressure and you would subtract the height of the column of mercury. If you have a situation where the pressure of the gas is greater than the pressure of, or greater than atmospheric pressure, in that case, you're going to add atmospheric pressure to the height of the column of mercury. So this scenario right here, this is what we saw here. Okay. And now she's saying in the slides, okay, well, when you have an open tube, you can have the other scenario as well. Okay. Again, if you're like, oh boy, which one, when do I add? When do I subtract? Personally, I think it's, in order for this concept to crystallize in your mind, it's a lot easier to just look at some examples, and then it usually becomes abundantly clear about what you've got to do. Okay, let's take a look here. It says, what is the pressure of the sample of gas trapped in an open tube mercury manometer shown below if atmospheric pressure is 736 millimeters of mercury and the height of the column of mercury here, the height is equal to 9.2 centimeters, which is the same thing as 92 millimeters. of mercury. Excuse me. Well, since the mercury is higher on this side than it is on this side, that tells us that the pressure of the gas, right, the pressure of the gas must be less than atmospheric pressure, right? It doesn't have what it takes to push against it hard enough. It must be less than atmospheric pressure. And so we're in this scenario right here. So what are we going to do? We're going to take atmospheric pressure and we're going to subtract the height of that column of mercury. Okay, let's plug in some numbers. We're going to have our pressure of our gas being equal to 736 millimeters of mercury, and we're going to subtract the height of the mercury, which is 9.2 centimeters. We'll convert it. We know there's 10 millimeters in every 1 centimeter. Okay, so that's the same thing as 736 millimeters of mercury, and this is also millimeters. Shoot. This is also millimeters of mercury. So subtract 92 millimeters of mercury, and you get that the pressure of the gas is going to be 644 millimeters of mercury. Like that. There's the pressure of our gas. Okay, so you can see again how that would lend itself to one multiple choice question on the next exam. Again, how did we know that the pressure of the gas was less than atmospheric pressure? Because the height of the column of the mercury was higher on the side of the gas than it is over here, right? The pressure of the atmosphere must be more because it's pushing it down more on this side, right? If the pressure of the gas was higher, then the height of the mercury would be higher over here. Okay, excuse me. Let's try one more problem that deals with a manometer, and then we'll move on to some relationships with gases. Okay, so it says here, on a certain day, the barometer in a lab indicates that the atmospheric pressure is 764 torr. Remember that 764 torr is the same thing as 764 millimeters of mercury, because a millimeter of mercury is equal to 1 torr, okay? A meter stick is used to measure the heights of the mercury columns above the bottom of the manometer. So this part right here, this is the bottom of manometer. All right. So we measure the heights of those columns. The level of mercury in the open-ended arm is 136.4. So that's this entire distance here is 136.4 millimeters. And this one over here on the arm in contact with the gas is 103.8 millimeters of mercury. All right. What is the pressure of the gas in atmospheres? Well, since the height of the column of mercury is greater on the side that's open-ended compared to the side with the gas, that tells us that this scenario, the pressure of our gas is greater than atmospheric pressure, right? It's pushing back harder or pushing harder than the atmospheric pressure can. And so the scenario that we have is this one here. So what are we going to do? Well, the difference between those heights, if you take your calculator and you take 136.4, subtract, I hope this works out, 103.8, you end up with, well, that's not right. What's going on here? That must be a typo on my Slido. I don't know where this comes from. I don't know if I copied this from another slide or something, but the difference isn't going to be 25 centimeters, because if you take delta H, it's going to be equal to 136.4 millimeters, subtract 103.8 millimeters, and you end up with 32.6 millimeters. Sorry about that. Anyhow, but you can see the difference here. The delta H is equal to 32.6 millimeters, and it's millimeters of mercury, if you want to think about it that way, right? Because it's a column of mercury. So what are we going to do to calculate the pressure of our gas? We're going to say the pressure of our gas is going to be equal to the atmospheric pressure, which was 764.7 millimeters of mercury. and then we're going to add the 32.6 millimeters of mercury, and then we get that the pressure of our gas is equal to 797.3 millimeters of mercury. All of the answers are given in atmosphere, so we'll just convert those into atmospheres. We have 1 atmosphere is equal to 760 millimeters of mercury, and those units cancel, and we end up with the pressure of our gas as being 1.05 atmospheres, like that, 1.05 atmospheres. All right, so again, if we go back here to summarize, when you have the pressure of your gas being less than atmospheric pressure, what do? You take the atmospheric pressure and you subtract the height of the column of mercury, okay? So this delta H right here. And when the pressure of your gas is greater than atmospheric pressure, then what do? You're going to take atmospheric pressure and you're going to measure the difference, the delta H, which is this right here, the difference in the height of the column of mercury. There we go. Okay, well, that summarizes manometers. Again, that's a lot more detail than you find in our textbook. Give me a thumbs up if you're like, yeah, I think I understand it. Even if you're part of the way with me, you're going to have to practice it a little bit, but if you understand, good. Thanks, Anthony. As long as you understand the concept, the idea. It's one of those things I'd say, some concepts in chemistry can be explained very, very simply. Other ones, the students are kind of have to think about it themselves a little bit before they'll really begin to understand it. And I'd say this is probably falls somewhere in the middle. Anyhow, let's switch gears. So let's take a deep breath. We're going to do something completely different here. Done. Okay. Now this is kind of a funny picture here. It's a figure that I just copied straight out of our textbook. It says this is what we call a J tube. You can guess why. It's a tube. It's in the shape of a J. Anyhow, you've got this, and we use a J tube for studying the relationship between pressure and volume. Okay, pressure and volume. Well, let me show you what's going on here. So you've got some mercury in the J tube here, and you can see that the height of the mercury on both sides is equal. Okay, and then we have a certain amount of gas in here, and it takes up a certain volume, right? The volume is equal to 100 milliliters. All right, so the effect that's being felt here is just regular old atmospheric pressure, right? That's this here, which would be around 760 millimeters of mercury. So what they're saying here is when you go from this tube to this tube, pressure is doubled. Okay, they're adding another 760 millimeters of mercury. So they're, excuse me, they're doubling the atmospheric pressure. What happens when the pressure is being doubled? Can anybody see what's happening to the volume? If you double the pressure, what's happening to my volume? It's not a trick question. It decreases by how much? If the pressure is doubled, the volume is decreasing by half, right? So when pressure is doubled, volume is cut by a half, cut to a half, okay? Now what happens if we go from the first tube to the third tube? They've added 2 times 760, and so here we see that the pressure is tripled, okay? And what happens to the volume when we go from here to here? The volume is a third, okay? So the volume is now a third. Maybe I should have written this as volume. I'll make it simpler. Volume is, there we go. Volume is a half, and then volume isn't. So if you double the pressure, the volume gets cut by a half. If you triple the pressure, the volume gets cut by a third. What's the relationship? We see that we have an inverse relationship between pressure and volume, right? And if you're like, what the hell does that mean, Mr. Dion? That shows the inverse relationship. What that tells me is that if the pressure goes up, the volume goes down, right? As the pressure increased, what happened to the volume? It decreased. If I go in the reverse direction, we're going to see the exact same thing. If the pressure decreases, the volume is going to increase. That's what an inverse relationship is. Okay? Now that inverse relationship is interesting if we make a plot of it. What if we plot a bunch of pressure, measurements of pressure of a gas versus volume? Well, somebody's already thought of that. Okay? And here's a here's a plot of pressure versus volume shown right here. And you notice that what happens if we go from a pressure of 0.6 atmospheres, okay, it's got a volume of 2 liters. What happens if we decrease the pressure by a half? The volume is going to increase, right? And I could have said it the opposite way. Look, if you double the pressure, what's going to happen to the volume? It's going to be cut by a half. Right? So that's the relationship we saw on the last slide. But the problem with this, I mean, there's no big problem, but the problem is that when we have a plot that's nonlinear, it's not really handy, right? It's really difficult to make predictions off of a plot that's nonlinear. But what happens is that if we plot the pressure versus the inverse of the volume, so pressure versus 1 over the volume, then we get a straight line. Okay. So if we take the pressure times the volume at any point along here, okay, we're going to end up with a constant. Let me prove it to you. If you take the pressure, 0.6 times 2. So if you take your calculator and take 0.6 times 2, you get 1.2. What if you take 0.3 and you multiply it by 4? So 0.3 times 4, what do you get? 1.2. So you get a constant, right? So pressure times volume gives us a constant. And we can plot, or we can make a relationship. We can say, well, I can choose any 2 points anywhere along this graph, okay? And what can I say? I can say that P1 times V1 is going to be equal to P2 times V2, and that is called Boyle's law. Okay, so Boyle's law is P1 V1 is equal to P2 V2. You must know this law. Okay, you must know its name. You must know who it's named after. Susan Boyle. She won America's Got Talent a number of years ago. Anyhow, you must also know that that Boyle's law holds true at constant temperature, so when temperature is not changed, and when the amount of gas remains constant. N represents number of moles, okay, which is the same thing as saying amount in chemistry, right? Okay, so Boyle's law, P1 V1 is equal to P2 V2. Maybe you could write it down on a piece of paper, put it somewhere important, but you've got to know Boyle's law. Everybody who takes chemistry 111 has to know Boyle's law. If you ever get lost on Boyle's law, just think about breathing, okay? When you inhale and exhale, you're seeing Boyle's law in action, right? So if you breathe in, okay, what's going to happen? The volume in your lungs increases, so then the pressure is going to drop inside, and so air is going to go into your lungs. What happens when you blow out, right? When you exhale, right? You exhale, the volume of your lungs is going to go down. Nothing more complicated than that, okay? Very simple concept. Now that we've looked at Boyle's law, and we'll look at some examples of problems that deal with Boyle's law, but I want to talk about some other relationships that involve pressure, volume, temperature, and the amount of a gas. What if we were to look at the relationship between volume and temperature? And this is a law that I find is intuitive to many students. A lot of students, can predict what's going to happen. If I was to just show you this and said, what would happen if I heat that up? A lot of students are just going to say, well, the gas would expand, and you're 100% correct. Okay, so this is just a really small piece of tubing. You guys have all seen capillary tubes now that you've done well, some of you maybe haven't if you're in group B, but capillary tube is just a really small piece of glass. And if you have some gas trapped in the bottom with some mercury on top, and it's at a low temperature, and then what happens if you heat that up? The gas is actually going to expand, okay? And there's a good reason for that. We're not going to get into the whole nuts and bolts as to why, but we see that volume and temperature are directly proportional. What does that mean? It means as the volume goes up, the temperature is also going to go up. If the volume goes down, the temperature is going to go down, right? That's the relationship between pressure and volume. Of course, this law or this relationship only holds true when n, the number of particles, is constant, okay? And when pressure is constant, okay? All right. Well, what if you make a plot of volume versus temperature, right? I just told you on the last slide that volume is directly proportional to temperature, it says it right here, okay? Well, if you make a plot of volume versus temperature, here we have volume on the y-axis, here we have temperature in Celsius on the x-axis. If you do that plot for a gas at a bunch of different pressures, let's say you did it, at atmospheric pressure, oops, I didn't do that, at atmospheric pressure, then you did it in Colorado Springs, then you did it on top of Mount Everest, then, I don't know, you did it, whatever, you just changed the pressure. Well, what's interesting is that the slope of the lines are going to change at different pressures. But look what happens is that if you continue the line, okay, if you take these lines and draw them all with a ruler, you notice that they all converge at the same point right here. Okay. Now you might be wondering, well, why is this line why do they all become dashed down here? Why isn't it just a solid line? The reason why is because gases condense once you get to a low enough temperature, right? They're not going to be gases anymore. So this is extrapolating the line, but what you end up with is, or what you see is that all of these plots are going to end up at the same point. And this point is what we call, oops, I need a different color pen here. We call this absolute zero, absolute zero. And this is a theoretical temperature where there is no molecular movement whatsoever. Electrons don't move, nothing moves, no matter moves at all. And it's defined as what we call absolute zero is 0 Kelvin or negative 273.15 degrees Celsius. Now we looked at the temperature conversion way back in chapter 1. This is chapter 1 material, but now you kind of see where it comes from. And Lord Kelvin is the one who made that discovery, and that's why the absolute temperature scale is named after him. Anyhow, but let's get back to this law here, that volume is directly proportional to temperature. Well, we could also say that volume is equal to, right? Volume is equal to some kind of constant times the temperature. Or we could say that volume over temperature is equal to a constant. Now, if that constant remains constant at a constant pressure, constant number of moles, we can develop this relationship here. V1 over T1 is equal to V2 over T2. Now, pay attention to me here for a second, because this is kind of splitting hairs, but there's a difference between the way these are named in this class versus Chemistry 101, and it's because they use two different textbooks. So if anybody in this class is taking Chemistry 101, and I'm not sure if anybody has or not, but in that class, what they call Charles' law is this: V1 over T1 is equal to V2 over T2. What they call Gay-Lussac's law in Chemistry 101 is P1 over T1 is equal to P2 over T2. In our class, in the Chang textbook, he calls all of these laws, he calls both of these laws Charles and Gay-Lussac's law, okay? So he gives them both the same name, which is kind of goofy. It makes it harder to separate in your mind. So sometimes I might call Charles' law and call it like this, and then Gay-Lussac's law, this one, okay? But the main thing is that you understand the relationships, okay? Anyhow, there we go. So we've got our relationship between volume and temperature, and we'll talk about Gay-Lussac's law in more. Do I have a slide about Gay-Lussac's law? No, I guess I don't. Okay, well, let me talk about Gay-Lussac's law for a second, because I don't have a slide that deals with, hold on. I thought I did. Yeah, I do here, so I do in a little bit, so I'll talk about it in a second, okay? Anyhow, where was I? Here we go. So, again, we have constant pressure, constant number of moles, and we see that volume and temperature are directly proportional, and that gives us Charles' law, V1 over T1 is equal to V2 over T2. At constant volume and number of moles, maybe I'll use a different color. constant volume and number of moles, we see that temperature and pressure are directly proportional. And we get this relationship P1 over T1 is equal to P2 over T2, like that. So as pressure increases, as you jack up the temperature, pressure is going to increase, right? If you've ever used a pressure cooker, you know that, right? You turn up the pressure or temperature or the heat on your stove. What happens inside the pressure cooker? The pressure increases. You lower the temperature, the pressure decreases, right? Okay. And then the next law that we want to look at is what's called Avogadro's law. And Avogadro's law deals with the relationship between volume and number of moles. And the law is simply this, that volume and number of moles are directly proportional. Now that probably makes sense to you. You might be thinking, well, come on, Mr. Dion, of course that makes sense. If you have more of something, right, if the number of moles of your gas increases, right, then it should take up more space. Yeah, absolutely. That's 100% true. So look, we have some kind of gas in this container here. You see we have 1, 2, 3, 4, 5 particles, right? What happens as we add more particles? Remember, temperature and pressure is the same for all of these. Okay, so if we maintain the pressure and the temperature constant, the more particles we have, we see that the volume goes up, right? If we increase the number of particles even more, the volume goes up even more than that, okay? And when we're looking at balanced equations that deal completely with gases, we have hydrogen gas, nitrogen gas, and ammonia gas. Well, again, you see that Avogadro's law is that volume is directly proportional to the number of moles of gas, or number of particles of gas. Notice that the the identity of the gas is not specified. So we'll put here identity of gas not important. Important. So that means any damn gas that we've got, hydrogen gas, nitrogen gas, ammonia gas, carbon monoxide, carbon dioxide, sulfur trioxide, helium, neon, I don't care what it is, okay? No matter what the gas is, this relationship holds true, okay? So if I have 3 moles of hydrogen, let's say you have 3 moles of hydrogen, okay? That's going to take up 3 times as much space as 1 mole of nitrogen, right? Because the volume is directly proportional to the number of moles. It doesn't have anything to do with molar mass. You might think, oh, come on, Mr. Dion, hydrogen is smaller than nitrogen. They're going to take up less space. There must be some kind of calculation. No, 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 okay? Read my lips. It's only got to do with the number of moles. More moles, more volume. I don't care what the gas is. I don't care if it's heavy or light. Doesn't matter. Okay, so if I have 3 moles of H2, it's going to take up 3 times as much space as 1 mole of N2. Now, when they combine, they only make 2 moles of ammonia, and so we only make up or take up this much space. So overall, if we look at the total volume on this side and the total volume on this side, the total volume on the product side, total volume is half, right? It's a half of what you started out with here, all right? The half of original total. All right, give me a thumbs up if you follow me on that concept. It may not be intuitive, but it's the law, okay? We have to obey the laws in this class. All right, I know we're kind of running late here because I know if you're in Group B, you have you have to show up to the lab, and I'd like to give my students enough time to do that. But I really wanted to get to this slide with you, okay? Just get here with you today, and this is a summary of the gas laws. There's a law that's not on here, okay? But let's just review them together as a group before we call it a day. The first one is Boyle's law, okay? And if you're wondering about all this NRT and stuff, don't worry. Next class, I'll talk about this even more. But what was Boyle's law? Boyle's law was that pressure and volume are inversely proportional. We said that P1 V1 is equal to P2 V2. Again, pressure is inversely proportional to volume. Then for Charles' law, the one that deals with volume and temperature, I called that one Charles' law. Here they call both of these Charles' law. But again, excuse me, the relationship between volume and temperature is that volume and temperature are directly related. So we have volume 1 over temperature 1 is equal to volume 2 over temperature 2. Again, I like to call this one Charles' law, and that's because our Chemistry 101 textbook does that at PPCC. Okay, when we look at the relationship between pressure and temperature, we see that pressure is directly proportional to temperature. As pressure goes up, temperature goes up, temperature drops, pressure drops, right? So we have P1 over T1 is equal to P2 over T2. And this is the one that I call Gay-Lussac's law. It's just easier to try to distinguish between them. But again, in our book, our author, Raymond Chang, he defines both of these as Charles' law. And he calls them Charles and Gay-Lussac's law is what he calls them in the book, okay? Now, again, there's one more law that's not on here. So, plus, there's Avogadro's law. So, Avogadro, it's the same Avogadro of Avogadro's number. So, Avogadro's law is that volume is directly proportional to the number of particles. And we can also write that as volume 1 over number of particles 1 or moles 1 is equal to volume 2 over N2, like so. All right. Well, with that in mind, we are kind of late here, so I don't want to take up too much time because we have to get to the lab. But what I would like you to do before coming to class on Thursday is let's take some time here. Let's look. I want you to try all these. I want you to read. Make sure you read through all these things. Ideal gas equation, ideal gas law. You know, you could read and try all of these problems. This one I've made it up in like 1,000 slides here. All the way up to jeepers. Yeah, I would like to at a minimum try to get to example 5.9. Okay, that would be a minimum. I would like you to try to at least read up to there, try all the problems up to and including example 5.9. Now we're going to take a look at the examples on Thursday, but I'd like to go through these examples kind of quickly because we've covered the main points. And then it will allow us to have more time to focus on gas stoichiometry, which is definitely a more, I would say, a more complicated topic, okay? And so I want to spend some good quality time with you guys discussing that, okay? So again, before you come to class on Thursday, I always encourage my students to read the entire chapter and try as many problems as they can, but at a minimum would be to read and try all the problems up to here, okay? Again, a bare minimum. All right. Well, let me just stop recording here. And I'm just going to double check.